There we go.
Again, you're just coming in, this will be just like the lab. These are the exact quantities. You're gonna add about half a gram in each. So if you want to got this down to shit nice, you do the lab pretty well and get a good review for us as well. Oh, you guys. Why that screen is not working? Yeah, I can just see our screen. You guys might have to move over this way. I don't know why that screen's not on.
Does, but I don't know if she comes every day. There's a new roll sheet going around, everyone, somewhere, single-sided roll sheet. Somewhere. Again, if you're just getting in, this is a good review for lab. This is the exact lab this week. Do I have this quiz due Wednesday and the owl both Wednesday or Tuesday? Wednesday night, that's right. That should be fine. All right, 9 o'clock, let's get started. Hopefully everybody had a good spring break. One of our students got stuck in Ireland, tested positive, so has to quarantine for a week. I'm not sure how that works, but I don't know. Could be expensive staying an extra week, I don't know. So hopefully everybody had a good spring break. The rest of the semester is going to go fast. I did a new roll sheet last night, and I think I noticed like Wednesday, maybe last date on there is the final. May 18th, I think it is. I think it's May 18th, 8 a.m. or something like that. So these 8 weeks are going to fly by for us. So what we need to do today is, I'd like to review this because it kind of reviews limiting. This, again, this is exactly your lab. So this will give us a review. We'll talk a little bit about pH, and then we've got 3 problems to finish is all. And then we should be done. All right, so let's climb into this here. So this is our lab. You're going to react solid zinc with solid iodine, and it's really good. It's a pretty good lab. But let's not kid ourselves. You're supposed to figure out the empirical formula here for X and Y. It's kind of like we've done in the past, but what's the only charge zinc can take on? And what's the only charge iodine can take on? So we're looking to get hopefully this. Right? I mean, that's the only possibility we can get. But it says to add about 0.5 grams of each. So if you add about 0.5 grams of each, let's calculate how many moles that is up here. So if we have 0.500 grams of zinc, and what do we got? 65.41 grams. And that would be our starting moles of zinc. And for iodine, we have obviously, you're not going to wait for the balance to get exactly 0.500, but I think it says between 0.4 and 0.6 or something like that. And then we have I2. This is going to be 253.81. Yes, 253.1 grams. So this is our starting moles. So this is what we have for moles of each. You know what makes it nice is everything here is 1 to 1. So we need 0.007644 moles of iodine. This is what we need. And if we figured out iodine first, if we went this way, we would need the same amount here for zinc. So once we get here, which one's limited? Your iodine is limiting, right? And for this reaction, you're going to see, you probably know what tincture of iodine looks like betadine before surgery, that type of stuff, or maybe your grandma's got tincture of iodine, I don't know. But this reaction will go clear. And when it goes clear, all of your iodine is used up. So iodine for sure here is limiting because, boy, you need almost 4 times that, right? So we know that this is limiting. And we know that the zinc is in excess. So the question is, how many moles of the reactant in excess are left over? And up here, this is my excess. So this is going to be my moles left over right here. If I subtract these, and if I subtract these, I am going to get 0.005674, I believe. 0.005674. Now this is excess zinc. Let's just actually, if we got room, excess zinc. And for this lab, you actually keep track of everything. So again, you're going to swirl this around in a flask. It's going to go clear when all the iodine is used up. So it works out pretty slick. So how many moles is right here? How many grams of the reactant in excess are left over? So we can just take those moles that we just found. And then 1 mole of zinc is 65.41 grams. And we know this has got to be less than 0.5, right? We started with 0.5. We want to know how many grams are left over. Make sure your answers make sense. And this is 0.3, 0.371 grams of excess zinc. All right. Now that's this. How many grams of zinc? I know it's Zn2 plus you end up with, but it's zinc in the product, ZnXIY, in our product. Well, if we started with 0.5 and we've got 0.371 left over, we're just going to subtract that, right? So whatever you start with, we have 0.5 grams minus excess of 0.371 grams. That means that we consume to product what do we get here? Help me make the math. That's a correct 0.129, right? 0.129. How many grams of iodine in the product? 0.5, right? Because it was limiting. Now, you're going to actually have real grams that you're going to calculate the empirical formula in lab. So you'll have some experimental grams here, but at this point, we could just take, to calculate the empirical formula now, we could take our 0.129 grams of zinc and convert it to moles, and our 0.5 grams of iodine and convert to moles. And I guess, let's see, 65. Well, this is going to come out to be what we had up above. And the next one is, we've already got this one, but I'll repeat it. That comes out to be perfect. Right, you get this, we got the same number here. It should. No, it should not come out perfect. It should come out 1 to 2. Oh. This should not be I2 down here. That's why. This should be I1. My bad on this. Let's see, that is going to be pumped that up. Yes, this is just iodine in the product, not I2.
Just 1 more of I2.
Yeah, it's 1 mole of I2, so 1 mole of, that should be just 1 mole out of here, my bad. So that is 126.90. Away. So now we got 0.003940. So now it's going to work out. This is mole of I. Mole zinc. Yes.
For that one, could you do it the way you did it originally though? Because it tells you it has 1 mole of I2 and then comes up with the same formula.
I guess if you did it I2, it's not how, yeah, if you kept it as I2, I guess, but it really doesn't exist that way.
Okay.
So we get a 2 and a 1, which is what we should get.
Okay.
Now you're going to have your experimental grams here that you're going to do. It's going to be your experimental grams. And this one is going to be grams of iodine consumed, so that should match because it's limiting. So that gives you an idea of what you're going to do for lab. And it works out pretty well. It does work out pretty well because you're keeping track of everything for the lab. Okay, so that I just made up just to review for that. Let's look at just a little bit about pH, and there was 2 videos that I linked, and a couple reminders because I still seem to see it all the time. The videos would have had this is exactly what it looked like from the video. This is the exact sheet. Now, a couple of reminders. You're never putting in times 10 in your calculator, right? So if you have a graphing calculator, this one has the EE right here, or you maybe got to do second to get EE. This one just has it right here, which is why I like the TI-30XA. It's really, really simple. And then this one here has the EE right here. So you have to do second if you have a TI-30X2S. So remember, just a reminder, you're not putting in times 10. So what I'd like to do is we have the last 3 problems to do. So I'd like to just do these, and then at the end, I'd like to set up whatever time we have remaining. I'd like to set up your quiz questions for you. And kind of looking on. So, okay, so let's look at this. These are titrations. So titrations, and you're going to do a titration in lab. And it is just a neutralization reaction. So you're going to have an acid plus a base. You're going to get a salt and water. So here's what this problem looks like. You're going to start with 125 milliliters of 0.0100 molarity calcium hydroxide. It wants to know how many milliliters of 0.0105 molarity hydrobromic acid would you add so that there's nothing in excess, nothing left over, and you have everything converted to product? Right? So how many milliliters do we put in? Now, remember, I always said that if you're adding milliliters, you're adding moles, and if you're adding moles, you're adding grams. So when you're dumping in a certain number of milliliters of solutions, you're really adding grams together. And the nice thing about this stuff is you don't even need a periodic table. So in this case, what do we always got to do? We got to get moles. So let's get moles right here. So our starting is, if we convert that into liters, we should have 0.125 liters. So this is 0.125 liters of solution. And the molarity is 0.1 mole per liter of solution, right? So my moles here is 0.00125. Okay, and then it's a 2-to-1 ratio. So in order to neutralize this perfectly, 2/1, right? Wherever I point my arrow, 2/1, I'm going to need to add 0.00250 moles. And again, we know that's moles. Now, the question is, when I bring this down, again, we know that this is in moles. When I bring this down, am I going to flip those units or am I going to keep it the same? What is molarity? It is moles over liters, right? I need my moles down below. So I need to flip these units. So I'm going to put 0.0105 mole down below, and I'm going to put my liter of solution on top. And then we need the answer in milliliters. I kind of like doing this, cross out liters, we just change it to 1,000 milliliters. Save yourself a step. So it looks like, what are we gonna, I don't know what we're gonna get. We're gonna get 238. Anybody calculate 238? No, 238. I think it's 238. Again, we're doing solution stoichiometry. It's just an acid-base reaction, so it's called titration. It's kind of nice. You don't need your periodic table. because we're dumping solutions together. Okay, the second one is a classic example of a lab calculation to calculate molarity of one of those two solutions when one is known. So for the next example, consider a neutralization reaction in which 75 milliliters of calcium hydroxide solution is neutralized with 5 times 10 to the minus 2 molarity HCl. And it requires 36.6 milliliters of the HCl. What is the molarity of the calcium hydroxide? When we get all done, all we got to get is moles over liters, right? That's what we're looking for. Well, we have enough information here to get moles of HCl. So my starting moles of HCl is going to be right here. And again, we don't need a periodic table. Point 0.0366 liters of solution. And 0.05 mole per liter. So it looks like point 0.00183. And then how many moles of calcium hydroxide is it going to take? My mole ratio fraction is 1/2. So if we split that in half, we are going to get 0.000915. And we know that's in moles. And to get molarity, we need moles per liter. So we already got moles, draw a line. This is how much solution it took. It took 0.07500 liters of solution. Which is a molarity of 0.0122 molarity. Okay. And the third one here looks to be similar to the first one. So what do we got here? What volume in milliliters of 0.15 molarity solution of potassium hydroxide would be required to titrate 40 milliliters of a 0.0656 molarity H3PO4 dephosphoric acid. So let's get this in moles. Point 0.0400 liters of solution. And the molarity is 0.0656. Let's see, what do we got here? 3 sig figs in that molarity. We'll keep an extra one here. So it looks like my starting moles is 0.002624 moles. Is that right?
Yep.
So then my mole ratio is 2 to 1. So it's going to take double that, or 0.0052485248, and we know that's in moles. We need to flip this again, right? Otherwise, we're going to end up with mole squared. So we need to flip this. So I'm going to write flip, I guess. We're going to flip that. I don't know. It looks like FU to start out. I don't know. That all sounds so good. That's ugly. I think I'll just write it right here. How about flipped? I'm going to write flipped now. Maybe that's better. So this is 0.1500 mole down here then. Liter of solution up here. And a liter of solution, let's just change that to 1,000 milliliters. And if we do that, we crank that through, we're going to end up with 5.248 divided by 0.15, 35 milliliters. 35 milliliters. So this comes out to be 35.0 milliliters of solution. Okay, now, go to quiz. Let's lay out the rest of this quiz because there's some limiting on that quiz. Let's see if I can write small. Let's see if we can lay these out for you as best we can and see what we got. All right. April 19th, 1995. Bomb exploded, killing 168 people, wounding hundreds of others, destroying the Alfred P. Muir Federal Building, Oklahoma City. The explosion mixture used in this incident contained ammonium nitrate, which is commonly used as fertilizer. What is the molarity of concentrated nitric acid if it takes 5.63 milliliters of the acid? Okay, so we're looking for, right, kind of small, we're looking for molarity of this nitric acid. And it takes 5.63 milliliters. Look at this. There we go. And here it took 15 milliliters and 6 molarity. So you should be able to go moles here. Moles here. And then if you want molarity, you're just going to want moles over liters, right? Moles over liters. So that should lay out 16. In 17. Let's see what 17 looks like here. So we've got how much HGS forms when, so it looks like we have calcium sulfide plus mercury 2 nitrate. So this is double replacement. Mercury takes the place of calcium. I'm going to actually have to write it. I'm going to go this way first, I guess. So we're going to end up with HGS plus calcium nitrate. Let's put in our oxidation states. So this is going to be a 2. And it looks like this is balanced the way it is, right? So this is a limiting problem. So what we're looking for here, how much H, this is in grams, we're looking for grams here. But we've got here this is 0.75 molarity, 113 milliliters. And this is 1.21 molarity and 52. No, I'm missing a sig fig there. I'm going to put 52.0 because all the answers have 3 sig figs. So I'll have to fix that. We're looking at something like this. Which again isn't so bad because we're going to get moles and moles to figure out which one's limiting. And we don't need a periodic table to get this much of it. So how many moles of this do we have? How many moles of this do we need? And then how many moles do we have? then this will give you your moles of HCS product. So liters times molarity, you get moles, right? I won't give you a formula for that. Just remember the units. Other teachers are going to give you a formula for all that stuff, but it doesn't make any sense. You just got to know what the units are. And you're trying to memorize some formula you don't need. So, okay, in 18, consider making silver chloride. How many grams of AgCl can be created? Let's see. Oh, we've got the reaction in this one. And maybe we can sneak this in there as it is. What do we got here now? So the molarity of calcium, this is, let's take this much. Oops, I better watch out. How many moles is this? Let's figure out the moles here. This is going to be 0.0655 liters, right? And the molarity is 0.125 moles per liter of solution. Oops, come on here, blow that up, please. Sorry about that. I'm gonna write this down below here where we got a little bit more room. I'm trying to calculate. How many grams of AgCl can be created? All right, this is what we're looking at here. One's on, I guess. So my starting moles here. So again, we have a limiting problem, so we got to figure out what we have, what we need. And my mole factor fraction here is 2/1. So we need 0.016. Yeah, 38, I guess. That's how much we need, right? And we can calculate how much we have. Because this was 0.025 liters of solution. And the molarity is 0.455. So you have 0.01138. So it looks like this one's limiting, huh? So if this is limiting, then that's going to dictate how many moles you get over here. You got to come off of what you have of the limiting. Draw your arrow. And my mole factor fraction is 2. Okay, let's see. We got a OH minus calculation there. We got a pH. We got 2 volts. Okay, let's set up 22, at least the reaction, and then we'll get all your reactions set up, I think, here. For 22, we have H2SO4. And that would be an aqueous solution plus NaOH. And these are just double replacements. I mean, they're neutralization. So think of hydrogen replacing sodium. So if that's the case, you get HOH, which is H2O, right? Liquid plus sodium takes the place of hydrogen. And then we need to balance that with we need 2 sodiums here, right? 2 sodiums and 2 waters. Right? The last reaction is, well, let's outline this a little bit. We got just enough time here to do this one and the last one here. Let's see what concentration. Okay, so we need molarity here. And 0.0100 liters of solution. And this one here is 0.20 molarity and 0.0078 liters of solution. And we got just enough time to set up 25, the last one. So if we set up 25, it's going to be the same reaction, except for instead of sodium hydroxide here, we have potassium hydroxide. So sulfuric acid is the same. So down in 25, we look like this. We're going to have H2SO4 plus 2 KOH. We're looking for the molarity here. Point 250 molarity here. And 0.0156. So that should help you out with the quiz. We'll answer a couple quiz questions on Wednesday. Right? We'll answer a couple quiz questions on Wednesday. I'm pretty sure I have chapter 5 ready, but look for an email from me before you print it or load it into whatever you use, okay? But I just want to look at it quick. And then we'll be working on chapter 5 on Wednesday. All right, have a good day. Stay out of trouble. Don't smoke, vapor, get COVID.